In this video, we're going to be talking about three-element control and how we use it in order to regulate just how much feed water is going to our steam drum and correspondingly how much steam we're generating and discharging from our steam drum. It's going to be quite a short video because the concept is relatively basic. The idea is just to give you a brief overview of what three-element control is, why we need it, and how it works. We're also going to discuss the topics of single element control and two-element control because they're a prelude to three-element control. And I'll explain to you exactly what swelling is and shrinking is, or shrinkage, with reference to the boiler drum. Let's start by having a look at a boiler drum. We've got a totally separate video on the boiler drum, so be sure to check that out. It's a lot more detailed than what we're going to discuss right now, and it's definitely worth a watch. Here is our steam boiler drum. I'll do a quick recap just of the important bits that are relevant to this video. You can see that the steam drum is long and cylindrical in shape. It may be up to about 2 meters in diameter. It may be up to about 30 meters in length. That's quite a large boiler steam drum. We've got our steam discharges on top and we've got our risers down below here. On the left side, we've got our downcomers. The downcomers distribute cold, or relatively cold, feed water to the boiler. That water will be heated up and then we'll get water and steam, a mixture of both, coming back up through these risers here. We're then going to separate the steam from the water in our steam drum and we'll discharge the steam back to the boiler where it will be further heated and we can then use that steam for driving a steam turbine. That would be one application, but you can, however, use superheated steam for different applications, such as within a given process. The steam drum sits at the top of a water tube boiler. This one here is a water tube boiler that would be used within a power station. The steam drum is located at the top over here. This design is different from the one we've just seen. The downcomers literally come directly out of the bottom of the steam drum, and they'll go off to our furnace walls, to the boiler, and then the risers will come back here. So that's a short introduction to the steam drum. As I say, there is a detailed video concerning the steam drum, so make sure to check that out if you want to learn a bit more about it. This video focuses on three-element control, so let's move on to that topic now. Before there was three-element control, there was single-element control. The reason we're even discussing single element control is because the feed water had to be sent to the boiler steam drum at the correct flow rate. If we send too much boiler feed water to the steam drum, and here is our steam drum example again here, the boiler feed water would come in through this pipe. You can see it's got holes all the way along. The feed water is distributed into the boiler steam drum. After being heated, we get our steam. It comes through this demister here and then out of the drum through the steam discharges. If there's too much water, we're going to get water carryover, which will go through this pipe here. That is our steam discharge outlet. And when we get that water carryover, we risk water hammer, we risk damage to our steam turbine blades, and we also risk that our heat transfer surfaces within the boiler become fouled. So we don't want that occurring. We want our steam to be clean. We want it to be dry. So that's a problem if we provide too much feed water to the boiler drum. If we provide too little feed water to the boiler drum, we're going to have a problem of a different kind. Then our downcomer pipes, here is one, are going to be starved of water. That means correspondingly, some of the tubes in the boiler will be starved of water. Remember, these are heat transfer surfaces. They may overheat because they're not being cooled down by the water. They may melt, they may rupture, and we don't want that either. So it's very important that our boiler feed water level stays within defined limits. As an example, it would stay roughly between where these two lines indicate now. This is actually quite difficult to achieve if you have a large boiler, multiple boiler feed water pumps, multiple loads, and large steam systems. Single element control is the most basic form of control used to regulate the feed water flow rate into the steam drum. To explain this as easily as possible, I'm going to go all the way back to the first designs that we used. Essentially what we had was a float within the boiler drum. The float would move up and down. As the float moved up and down, depending on where the water level was within the boiler drum, it would open and close a valve proportionally. So if the level was dropping quite quickly, the boiler feedwater valve would open quite quickly. As the water level in the drum increased, the valve would proportionally begin to close. So a very typical arrangement, and it's called single element control because we're controlling the feedwater flow rate using a single element. And this element is a level transmitter or a simple float like what I just described. Modern boilers, if they do use single element control, they will use a level transmitter, abbreviated to LT. The level transmitter will send an electrical signal to a controller. The controller will then regulate the feedwater control valve to regulate how much feedwater is sent to the boiler drum. So quite basic. That is single element control. What's interesting though is that measuring the level is not enough. We also need to measure the pressure within the boiler steam drum. Why? The reason is because the pressure within the drum causes the water level to change. A reduction in pressure within the drum causes the feedwater level to increase. An increase in pressure causes the feedwater level within the drum to decrease. Imagine for a moment that we suddenly get a very large demand for steam, and this steam needs to be taken from our steam drum. We get a reduction in pressure, and that leads to a corresponding rise in boiler feedwater. So we're measuring a rise in boiler feedwater, which tells our feedwater control valve to reduce the flow of feedwater to the steam drum. The problem here is that what we should be doing is increasing the feedwater flow rate to the steam drum. We should be opening the feedwater valve. So by measuring the level alone, it's not a very reliable way to know what the true level is within the steam drum. The reason we get this false signal is because when the pressure decreases in the steam drum, the steam bubbles that are contained within the feedwater in our steam drum expand. They become larger. This causes the level in the boiler steam drum to rise. It's not so much rising as expanding due to the reduction in pressure. But discounting all of that, what we've actually got now is a false signal. It looks like the steam drum has a high water level. We start to throttle the feedwater valve to close it, and that's exactly what we don't want to do, because this whole situation has only been caused by a sudden large demand for steam. So at this point, we should actually be feeding more feedwater into our steam drum. The situation that I've just described, where we get a false signal and the water level increases, is known as swelling, or the swelling effect. The opposite of this is where the feedwater level in the steam drum decreases as the pressure in the steam drum increases. This is known as shrinkage, or the shrinkage effect. So we must account for pressure in our steam drum if we're going to measure the level accurately. So we're going to have a level transmitter and we're going to have a pressure transmitter. We're going to feed those two signals to a controller. The controller is then going to throttle or regulate our feedwater inlet valve in order that we supply the correct amount of water based on the level in the steam drum and the pressure in the steam drum. That is single element control. Admittedly, when they talk about single element control, they discount the pressure transmitter. They only include the level transmitter and they call it single element control. But if we want to go a bit more deeper into it, you do really need to measure the pressure in the steam drum in order to get an accurate reading. Let's have a look now at two element control. Two element control is similar to what we had before. The difference though is that this time we're going to measure the steam flow rate, or the mass steam flow rate, in addition to what we measured when looking at single element control. So now we've got two separate elements of control, the mass steam flow rate and our level transmitter. The signal from our level transmitter and from our steam flow transmitter are again sent to a controller. The controller is then going to calculate what position the feedwater valve needs to be in, and then we're going to take corrective action to adjust the position of our feedwater control valve. This gives us a much more accurate way of controlling the feedwater flow rate to the steam drum. 3-element control goes a step further. We're now, in addition to measuring the level within the steam drum and the steam flow rate, we're also going to measure the water flow rate, or mass feed water flow rate. This is 3-element control because we've got 3 separate points of measurement. Remember, like I said though, that there is also the measurement concerning the pressure in the drum. Using this method, we can accurately control the feed water flow rate to the steam drum and ensure that the level within our steam drum stays within defined limits. It is not easy to keep the water level in the steam drum within defined limits if you're only using single element control. We have problems with shrinkage and swelling, and if we're using multiple boiler feed water pumps, if we're using turbine driven pumps, if we've got steam loads that cycle significantly from high demand to low demand, and they do this quite frequently, it's very hard to keep that water level in the drum within defined limits. You're dealing with all of the feed water going into the drum. You're dealing also with the steam water mixture that's coming back into the drum from the risers, these cyclic steam loads. And in addition to all of this, what you'll often find is that the feed water control system will be connected to the fuel system of the boiler in order to regulate the fuel proportionally with relation to the feed water system. As an example, if we start supplying more and more fuel to our boiler, it makes sense that our feed water control valve should open more and more. A control system will know this and will be able to take inputs from the steam flow rate from our steam drum, take an input from our feed water flow rate, also our level transmitter, certain other pressures and temperatures around the system, and then correspondingly we can regulate things like the fuel flow rate and the feed water inlet flow rate. So many factors here used to control the level within our steam drum. But it's very important that that level does stay within those defined limits, because any deviation outside of those limits could lead to damage on our heat transfer surfaces, pipes melting, pipes rupturing, water carryover to our steam turbine or processes, water carryover to our other heating surfaces such as the superheaters, and this may lead to things like scale developing on the inside of our heat transfer surfaces, such as inside the tubing, and this again will reduce the heat transfer rate for our tubes, which gives us an uneven thermal distribution across our heat transfer surfaces and increases the likelihood that we damage our boiler tubes. These are just some of the basic problems that we're likely to get by not keeping our steam drum water level within defined limits. This table gives you a brief overview concerning single, 2 and 3 element control. The part of the table that I think is the most interesting is the measurement row. Here you can see in the single element column, we've got 2 measurements, drum level and drum pressure. In 2 element control, we've got drum level, drum pressure and the mass steam flow. And in 3 element control, we've got the drum level, drum pressure, mass steam flow and mass feed water flow. Irrespective of what kind of element control we're looking at, the best kind of control is one where we control the mass balance of the steam drum. We know what's going into the steam drum, we know what's coming out of the steam drum, and our feed water valve can be regulated based upon that. A quick comment here concerning what element of control you'll use when you start the boiler. Typically, you'll only use single element control. This is because the steam flow rate is unreliable when we start the boiler. There's no point measuring the steam flow rate when we start the boiler because the signal we're getting will not be very accurate. When the steam pressure and temperature is increased and we have a relatively constant steam flow, then we can switch from a single element control system to a 3 element control system. The controller used for single element control and 3 element control will be the same controller, so we can do this seamlessly. We're not going to suddenly lose control for a second or two. It will happen instantaneously. Modern large boilers use 3 element control. You're not going to see single element control on a large water tube boiler. Some very basic old water tube boilers, quite small, may only use single element control. But this really is the absolute exception to the rule. 3 element control is standard for large water tube boilers. It's the most reliable way to ensure that our boiler feed water level within the drum stays within the defined limits that we want. And because it's so critical that that water level does not decrease or increase beyond those limits, manufacturers are willing to spend the additional money to install 3-element control. It's a safety feature and it is critical. Aside from that, it's also simply more efficient to operate the boiler with 3-element control than it would be if we used single-element control. If you want to use any of the 3D models shown in this video, then head on over to saVRee.com. We've got over 400 engineering 3D models that you can use directly through a web browser in AR or VR. If you want to learn more about engineering, we've got over 45 hours of engineering video tutorials and courses at saVRee.com, and you can learn about valves, pumps, power stations, electrical transformers, and many other common engineering machines and processes. Before you go, don't forget to subscribe to the YouTube channel. Thank you very much for your time.